Welcome to the next lecture on Synchronous Machines course. In the previous lecture, we discussed about basics of electromagnetic torque, and we concluded that there are three conditions to be satisfied for the production of electromagnetic torque. First one is stator and rotor must be designed for same number of poles. Second point is relative speed between stator magnetic field and rotor magnetic field must be equal to 0. Third condition is there should be a finite phase angle difference between stator field and rotor field. Now these three conditions must be satisfied for all kind of rotating electrical machines. That means for DC machine, induction machine as well as a synchronous machine. Okay, and also we developed the equation for electromagnetic torque. Torque is proportional to minus F1 F2 sine lambda. Okay, and where lambda is the angle between stator field and rotor field. Okay, that is clear. Now let us continue our discussion regarding the basics of synchronous machine. In the previous class itself, I discussed what is the basic difference between a DC machine and a synchronous machine. DC machine and synchronous machine will operate based on same principle, that is Faraday's law of electromagnetic induction. According to that, whenever a conductor is rotating in a time invariant magnetic field, it will experience changes in flux linkages so that an EMF will be induced across it. First of all, time invariant magnetic field means it can be produced by using DC current excitation or AC current excitation, DC current excitation. So therefore, I can write we are using DC excited field in case of DC machine as well as DC excited field in case of synchronous machine as well. In both machines, we will create magnetic field by using DC current excitation. And whenever conductor is rotating in this DC field, an alternating EMF is induced across it or direct voltage will induce across it, alternating voltage will induce across it. So AC voltage will induce across armature conductors. Okay. Similarly, in synchronous machine also AC voltage will induce across armature circuit, okay, or armature conductors. So the field is DC field, that means a time invariant field, but when the conductor is rotating, definitely AC voltage will induce across it. And also we developed a formula for frequency of that induced EMF. Can you tell me what is the frequency of that induced AC voltage across armature conductors? That is P into N by 120 Hz. Even in DC machine also same frequency formula is valid. But in DC machine, why we will not study about that frequency much? Because the reason is, even though AC voltage is induced, we will convert that AC voltage to DC voltage using the help of commutator and brush system. But in case of synchronous machine, our requirement is AC voltage output. Therefore, we won't use any commutator and brush system here. And also you tell me here, once the construction of the machine is completed, can I say number of poles are going to be constant? Therefore, frequency will be directly proportional to the speed at which the rotor is rotating. And we all know that in power system, our synchronous generators, also called as alternators, are expected to generate constant frequency voltage or variable frequency voltage, yes or not? And frequency will be a constant value only if rotor is rotated at a constant speed. That's why synchronous generators must be always driven by prime movers which are rotating at constant speed. And that constant speed is what we will call it as synchronous speed of the machine. In case if that rotor speed is continuously changing, definitely the frequency also changes. If frequency changes, system may lose its stability. So to generate constant frequency voltage, we have to rotate rotor at a constant speed known as synchronous speed. Very clear. But in case of DC machine, frequency doesn't matter. Whatever may be the frequency, we are converting everything into DC. Therefore, you can change the value of speed. Speed can be varied in DC machine but cannot be varied in synchronous machine. Okay. Next, coming to the major difference between DC machine and synchronous machine is, in DC machine, who is stationary and who is moving. I discussed already, these all points we already discussed, I am just recapitulating again. Okay. In case of DC machine, magnetic field is stationary. Okay. And armature conductors are going to be rotating. Armature conductors are going to be rotating. Whereas in case of a synchronous machine, armature conductors are stationary and magnetic field is going to be rotating. Magnetic field is going to be rotating. If I ask you the question, which is the easiest procedure out of these two, I discussed already, synchronous machine procedure is the easiest procedure. Why? Because in synchronous machine, armature winding is stationary. When winding is stationary, it is always very easy to collect the current from the winding. Okay, you can easily collect the current from the winding. But when the winding is rotating, when armature is rotating, collecting the current out of a rotating part is very difficult. Always arcing and sparking problems will be there. Even though arcing problems existed, why we are still using rotating armature winding only in DC machine? Yes, to satisfy commutator and brush system action. But in synchronous machine, commutator and brush system is not required. That's why it is better to keep winding stationary. If winding is stationary, there are a lot of advantages. In the construction part of the machine, I will tell you what are the advantages if armature winding is stationary. But the basic advantage is when the winding is stationary, it is easy to collect current from the machine. Understand? So these are the basic differences between DC machine and synchronous machine. What are the similarities? Both DC machine and synchronous machine we will use DC excited field. In both DC machine as well as synchronous machine, AC voltage will induce in armature and the frequency of that induced EMF is equal to Pn by 120. But in DC machine, that induced AC voltage will be rectified into DC by using a commutator help, but in AC machine we won't do that. And also requirement is to generate constant frequency voltage, therefore we have to rotate synchronous machine at a constant speed. That's why it is called as a synchronous machine. And the next difference is in DC machine field is stationary, armature is rotating, but in AC machine field is rotating, armature is stationary. But in both cases same EMF will be induced, that is called as dynamic induced EMF. Dynamic induced EMF. Now in this lecture let us go more details into the basic working principle of a synchronous machine, and we will also study basic relations between stator field and rotor field. Okay, all right, let us study about the basic working condition of a simple alternator. Okay, simple alternator is also called as a synchronous generator. Why the name is given as alternator? Because it is generating alternating voltage. That's why the name is given as basic alternator. Anyway, let me consider a simple alternator having only two conductors and a simple magnetic field. If you try to rotate the rotor, what happens is the discussion. Okay, look at this. So assume this is the stator magnetic circuit of a given synchronous generator. I told you in synchronous machine, armature winding is stationary, magnetic field is rotating. And that too, which type of magnetic field we have to use? DC excited magnetic field. Okay. Now, assume on this stator magnetic circuit, it is only a front cross-sectional view. The axial view you are not able to see. This is only front cross-sectional view. On this stator magnetic core, let me take one coil, one simple coil. Let us say this is A and this is A dash. Okay, we know a coil means two sides will be there. One side will be under the effect of north pole, the other side will be under the effect of south pole. What is the angle between this A and A dash? If you see this physical diagram, it looks like 180 degrees. That is called as full pitch. If it is less than 180, we will call it as short pitch. We will go to the details very soon. Okay, this is basic description. Okay, and it is stationary, don't forget that. Now this is the stator part. Now inside this machine there is a rotor magnetic circuit. You see, assume there is a simple rotor magnetic circuit like this. All right, and I told you we are using DC field excitation. Therefore assume this is the rotor and this is the rotor winding. You see number of turns are there, and this rotor winding is connected to a DC supply. Okay, you may have a doubt here, the rotor is rotating, yes or not, but this DC supply is given from outside. Externally we will give the DC supply. Externally means this source is stationary, DC source, but that winding is rotating. How to connect a stationary DC voltage to a rotating winding? Yes, by the help of slip rings. We studied in induction machine already. And here this DC supply will have how many terminals? Two terminals. One is positive terminal, another one is negative terminal. Therefore we need two slip rings. Okay, using the help of slip rings, this DC supply will be given to rotor. Anyway, according to the polarity, can I say this is the direction of DC current? And that DC current is what we will call it as field current in synchronous machine. We will call it as field current because this is a field winding. According to the direction of that field current, can you tell me what is the direction of field flux? Use right hand thumb rule. If you look at the arrow marks, this is the direction of field current. Therefore my thumb will show you the direction of field flux. Okay, it is in upward direction. Upward direction means you tell me this pole is emitting the flux or taking the flux? Emitting the flux. Therefore it will offer north pole polarity. Then this will offer south pole polarity. Okay. Now next important thing is this is DC flux, right? DC flux. And this is the rotor part. And as it is a generator, we are talking about a generator. Generator means it will rotate on its own or we have to rotate it. Definitely we have to rotate it using the help of a mechanical prime mover. That prime mover may be a steam turbine, that prime mover may be a water turbine, gas turbine, diesel engine, or you rotate rotor with your hands, okay, any hand pumped generators, okay, anything it may be. So using the help of a mechanical prime mover, let us assume I am rotating this rotor in anti-clockwise direction. Okay, in anti-clockwise direction. You rotate rotor in any direction. It depends upon the prime mover what you are using. I am assuming the rotor is driven in anti-clockwise direction. At how much speed we will rotate the rotor? I already told you. To generate constant frequency, we have to rotate rotor at a constant speed, and that speed is what we will call it as synchronous speed. Okay, synchronous speed. Now presently you tell me this is north pole and this is a south pole. What is the axis which is passing through the pole always? Yes, the axis which is passing through the pole is called as polar axis of the machine, also called as direct axis of the machine. Direct axis or polar axis both are same. And we also studied in DC machine already. Whenever a conductor is along polar axis of the machine, obviously maximum EMF will be induced in those conductors. Okay, so therefore I can say EMF will be induced in these two conductors. Now the question is how to find out the polarity of that induced EMF? Fleming's right hand rule. I explained in the previous lecture already. I am doing it again. According to Fleming's right hand rule, thumb will give you the direction of conductor movement. But here conductor is moving or stationary? Conductor is stationary, but field is moving in anti-clockwise direction. We studied already. Field rotating in anti-clockwise direction is equivalent to conductors rotating in clockwise direction. Therefore, I can take the relative movement here. Conductor is said to be moving in clockwise. Clockwise means this conductor is moving to the right side, this conductor is moving to the left side. So see here, this conductor is moving to the right side. North pole is emitting the flux. You see my point finger is showing the magnetic field emitting the flux. Then central finger will show you the direction of EMF, that is out of the plane or into the plane, definitely out of the plane. So this is a dot polarity. And obviously here a cross polarity EMF will be induced. This is the situation right now. Okay, so I can say, let us say this is starting situation, that is 0 degrees position. Okay, and conductor A dot polarity, conductor A dash cross polarity. This is reference point, that is 0 degrees position. Now you tell me after 180 degrees what happens? After 180 degrees means, can I say this rotor is rotating? After 180 degrees, this south pole will go to this side and the north pole will come to this side. So let me remove all these things. After 180 degrees, the rotor is rotating, isn't it? We are rotating the rotor. So south pole will go here and the north pole will come here. Okay. So why it is happening? Because we are rotating the rotor. Now tell me conductor A is under north pole or south pole? South pole. Therefore, the polarity will change from dot to cross. And here A dash is now under north pole. Therefore, the polarity will change from cross to dot. So after 180 degrees, conductor A becomes cross polarity, A dash becomes dot polarity. Next tell me, after one more 180 degrees means, can I say 360 degrees? Yes or not? After 360 degrees means you have to rotate it by one more 180. One more 180 means here north pole will come and here south pole will come. Now tell me conductor A is again under north pole. Under north pole we will get dot polarity. Under south pole here it will be cross polarity. So therefore now A is dot polarity, A dash is cross polarity. So like that you can rotate it by one more 180 degrees and polarity is changing every time. You see that? For every 180 degrees, can I say the polarity across the conductor is changing? That will definitely induce an alternating EMF or direct EMF, alternating EMF. So therefore, if I draw the coil voltage, okay, with respect to time, definitely it is going to be an alternating voltage. Okay, so I started with 0 degrees. After 180 degrees, the polarity reverses. After one more 180 degrees, again the polarity is reverses. Okay, so therefore, when you are rotating the rotor, okay, gradually with respect to time, okay, this is 0 degrees, I think. Okay, 180 degrees, this is actually the 0. Because we took 0 degrees as maximum EMF position, direct axis, right? Okay, don't always take this is 0. This is just our, theoretical example. But in our diagram, 0 degrees position means the first position, conductors are along direct axis. Direct axis means maximum EMF position. 0 degrees, this is 180 degrees, this is 360 degrees. So therefore, as the time progresses, the induced EMF polarity is changing. Therefore, an alternating EMF is getting induced. An alternating EMF is induced. Okay, this is the simple observation having only one coil. Assume that is a phase A coil. But a practical synchronous generator will be always designed for one phase or three phases. Now let me consider a simple alternator with three phases A, B, C. Our requirement is a balanced voltage has to be generated. What is mean by balanced voltage? Balanced voltage means there should be exactly 120 degrees phase angle displacement among the three phase voltages. 120 degrees phase angle difference. Okay. Now let us see a three phase simple alternator. Simple alternator means only one coil I am selecting. Practical alternator means number of coils will be available. Okay, that's all. Let's see what happens if a three phase alternator is selected. Okay. All right. Look at this. This is the stator part of the given synchronous machine. I have to accommodate three phases right now. And I am assuming every phase has only one coil. Simple generator I am talking about. Only one coil. Let us say this is phase A. Okay. Here we have A and A dash. A and A dash will form one coil of phase A. Next, B phase. As I told you, we need 120 degrees phase angle displacement. So therefore, from phase A, you move 120 degrees in space. Okay, 120 degrees. This is 180. I moved by 120 degrees. Let us say this is B and exactly opposite side we have B dash. And after one more 120 degrees, we will get C and here we have C dash. Okay. So this is a diagram where 3 phases are accommodated. Now some of the students may get a doubt here. I selected A here. If I move in anti-clockwise direction, I have B. Next I have C. You can also design the machine in other manner also. You select A here, B here, C here. No problem at all. Okay, there is no rule to select only in clockwise direction or only in anti-clockwise direction. There is no rule like that. But there is a rule, 120 degrees phase angle displacement is required, but in which side you are selecting doesn't matter. Okay, fine. Now you see this. Assume this is the rotor we have. Okay, I am selecting a 2-pole rotor. See, remember one point everybody, I already explained there is a relation between mechanical angle and electrical angle. Whatever you are seeing physically on the machine, that is a mechanical angle. But for mathematical expressions, we have to use always electrical angle. What is the relation between mechanical angle and electrical angle? Electrical angle is equal to P by 2 times of mechanical angle. Physical angle, whatever the physical angle you are seeing, that is always mechanical angle. And you have to convert into electrical angle to use in mathematical equations. Presently, I am selecting how many pole machine here for simplicity. For simple explanation point of view, I selected a 2-pole machine. If a number of poles are 2, can I simply write electrical angle is nothing but equal to mechanical angle? So, whatever the mechanical angle you are identifying right now, that is equal to electrical angle also. Suppose if it is a 4-pole machine, electrical angle will be equal to 2 times of mechanical angle. Okay. Now you tell me, when I said in a 3-phase system, we always need how much phase angle displacement from one phase voltage to another phase voltage? 120 degrees is required. That 120 degrees is always electrical angle, don't forget. Whatever we are using in power system analysis, power system mathematical equations, voltages, currents, flux, EMF, everything, it should be electrical angle only. Whatever we are seeing on the magnetic core physically, that is a mechanical angle. Okay. So always try to convert that mechanical angle to electrical angle. 120 degrees displacement should be always electrical angle. But as it is a 2-pole system, if you need 120 degrees electrical displacement, you need 120 degrees mechanical displacement as well. Okay, that's why from A to B there is 120 degrees mechanical displacement. Therefore, electrical displacement is also equal to 120 degrees. If I select a 4-pole machine, tell me what is the relation between electrical angle and mechanical angle? Yes, electrical angle will be equal to 4-pole machine, 4 by 2, 2 times of mechanical angle. Therefore, tell me, if you need 120 degrees electrical displacement, then you have to provide 60 degrees mechanical displacement. If you provide 60 degrees mechanical displacement, then only 120 degrees electrical displacement will come into picture. Okay? Catching the point. So therefore, it is always very important to select the mechanical angle to satisfy the required electrical angle. 3-phase voltages must be displaced by 120 degrees electrical always. Okay. So to avoid that confusion, I am always selecting a 2-pole machine, because in a 2-pole machine electrical angle, mechanical angle both are same. Okay. Alright. Now look at this rotor. We will excite this rotor with DC supply or AC supply. DC supply, and assume that DC supply created north pole here and south pole here. Okay. And as it is a rotor, we have to rotate it. You can rotate this rotor in any direction. Let us assume that I am rotating this rotor in anti-clockwise direction at a speed equal to synchronous speed. Okay, and write down where is polar axis and where is interpolar axis first. Whatever the line which is passing through the pole, this is a polar axis, also called as direct axis of the machine. The axis which is perpendicular to polar axis, this is nothing but quadrature axis or interpolar axis. Whenever the conductor is along polar axis, maximum EMF will induce. Whenever the conductor is along a interpolar axis, zero EMF will induce. Now, if this is interpolar axis, can I say above interpolar axis which pole effect right now? North pole. Below interpolar axis, south pole. Therefore, these three conductors are right now under the influence of north pole. These three conductors are under the influence of south pole. Clear? Next, which conductors will experience maximum induced EMF here? The conductors which are lying along interpolar axis or polar axis? Polar axis. Can I say right now A and A dash are along polar axis, therefore they will experience maximum EMF. How to identify the polarity of induced EMF? See, this is the 20th time I am discussing again to identify the polarity of induced EMF. Field is rotating in anti-clockwise direction. That means conductors are relatively moving in clockwise direction. So this conductor is moving to the right side. North pole will emit the flux. Induced EMF is out of the plane. Okay. And here it is going to be into the plane. These are the maximum EMF positions. Right now, phase A voltage is maximum. Okay. And assume this is the reference position, that means 0 degrees position. Let me write it here. 0 degrees position. Which phase voltage is maximum? Phase A. Okay. I am drawing a diagram here. You see, I am taking the time on x-axis and the induced EMF on y-axis. Assume this is 0 degrees position. Right now, which phase voltage is maximum? A. Phase A voltage is maximum. And if you continue to rotate the rotor, AC voltage will induce like that. Okay, very clear. This is 0 degrees. This is 90. This is 180. After 180, you see south pole will come here. So phase A voltage will change. Polarity will change from positive to negative. This is going to be 360. And again, after 90 more degrees, okay. 90 more means you tell me 360 plus 90, that is equal to 450. Like that, the order will continue. Presently, phase A voltage is maximum. Very clear. Next, tell me, as rotor is rotating in anti-clockwise direction, after how many degrees, which phase winding voltage becomes maximum? You see, if as rotor is rotating in anti-clockwise direction, can I say after 120 degrees, that north pole will come to phase B position? Let me draw that rotor diagram. Yes. This is going to be the rotor position after how many degrees? After 120 degrees. This is north pole, this is south pole. Okay. Rotor is rotating in anti-clockwise direction. Don't forget that. So I can remove the first position of the rotor. This is after how many degrees? 120 degrees. So now B phase will have a maximum EMF. I must remove A phase EMF as maximum. After 120 degrees, B phase EMF is maximum. Okay. Next, if you continue to rotate after one more 120, that means overall 240 degrees, can I say this north pole will come under the influence of C phase? This is north pole. Now the north pole is under the influence of C phase. This is after how many degrees? 240 degrees. So therefore, at 0 degrees, phase A EMF is maximum. After 120 degrees, phase B EMF is maximum. After 240 degrees, phase C EMF is maximum. This is all happening if I am rotating the rotor in which direction? Anti-clockwise direction. So at 0 degrees, A phase voltage is maximum. After 120 degrees, B phase. 120 degrees means, can I say between 90 to 180, here 120 will be there. Here B phase voltage is maximum. Okay. B phase voltage. Okay. This is phase B voltage is maximum. Next, after one more 120, that means at 240 exactly. 240 means between 180 to 300, somewhere here, C phase voltage will come into picture. This is C. So therefore, if I rotate the rotor in anti-clockwise direction, first phase A voltage is maximum. Next phase B. See, between A and B, C dash is also there. Okay. But we are concentrating on A, B, C. all right. So at 0 degrees phase A voltage is maximum, after 120 degrees B voltage is maximum, after 240 degrees C voltage is maximum. So what is the phase sequence you are able to understand here? Yes, first phase A voltage is maximum, next B voltage is maximum, next C voltage is maximum. After C, can I say one more 120 degrees, again A voltage, again B, C, A, B, C. Therefore, the phase sequence what you are able to get here is A, B, C sequence. We are able to get A, B, C sequence. That is nothing but positive sequence voltage will be generated. Positive sequence voltage is generated. Voltage is generated. Now, you tell me here what happens if I rotate the same rotor in clockwise direction rather than anti-clockwise direction. I am reversing the direction of rotation. Winding positions I can't change. Why? Because construction is already completed. Once the construction is completed, the position of the conductors we can't change. What is the only thing we can change? Prime mover rotation direction I can reverse. Let me rotate the same rotor in reverse direction. If I rotate the rotor in clockwise direction, you tell me now presently which phase voltage is maximum? A phase is maximum because A phase is along polar axis or direct axis. First A is maximum, very clear. After 120 degrees, you tell me which phase voltage becomes maximum because we are now rotating in clockwise direction. This is 120 degrees position. After 120 degrees, can I say C voltage is maximum? This time after 120 degrees, C voltage is maximum. After one more 120 degrees, that means at 240 degrees, which voltage is maximum? B voltage is maximum. After 240 degrees, B voltage is going to be maximum. So indirectly you tell me now what is the phase sequence we are able to get? A, C, B and then A, C, B, the order will continue. A, C, B means indirectly negative sequence voltage is generated. Negative sequence voltage is generated. Therefore, can you tell me how to reverse the phase sequence of voltage generation in case of a synchronous generator? Means what is the answer? Yes. Phase sequence can be reversed just by reversing the direction of rotor. If you rotate the rotor in anti-clockwise direction, we are getting ABC sequence voltage. If you rotate the rotor in clockwise direction, we are getting ACB sequence voltage. But the operating principle doesn't change, only the sequence is getting changed. Okay. So, how to reverse the sequence of voltage generation means by reversing the rotation of rotor. If you reverse the rotation of rotor, definitely the sequence of output voltage will also reverse. Okay, ABC sequence becomes ACB sequence. And one more thing, to generate balanced voltage. Balanced voltage means there should be 120 degrees electrical displacement among the three phase voltages. To create that 120 degrees displacement, we need 120 degrees displacement between the windings also. To have 120 degrees displacement between voltages, we need 120 degrees displacement between windings also. Suppose if you maintain rather than 120 degrees, if you maintain 110 degrees, what happens? The voltages will also have only 110 degrees phase displacement. 110 degrees phase displacement means it becomes balanced three phase or unbalanced three phase, unbalanced three phase. That's why construction is very, very important. During the construction itself, we have to take all measures to have 120 degrees mechanical or electrical displacement among the three windings, then only balanced voltages can be generated. Okay. So there is always a confusion between mechanical angle and electrical angle. What students generally feel is space angle means mechanical, time angle is electrical. That is absolutely wrong. Absolutely wrong. Space angle is nothing but a physical angle. Time angle is generally not a physical angle, it's a virtual angle we will use for voltages, currents and all. Space angle we will use for windings, slots, coils and everything. Now, space angle can be expressed in two ways again. Space angle can be expressed in either mechanical degrees or electrical degrees. Don't forget. Space angle can be expressed either in mechanical or electrical. Directly, if you look at the diagram physically, what is that angle? Mechanical space angle. Convert that mechanical space angle to electrical space angle. Okay, electrical space angle. If I ask you from this diagram, what is the angle between this conductor A and B dash? Immediately, a circle means 360 degrees mechanical. Okay, out of that, this is going to be 60 degrees mechanical. This 60 degrees mechanical is a space angle, right or not? But always in the mathematical equations, I must use mechanical space angle or electrical space angle. Electrical space angle I have to use. So convert this mechanical space angle to electrical space angle and use it in the mathematical equations. Okay. Suppose if I ask you what is the angle between phase A voltage to phase C voltage here. Voltage, currents, these are always expressed with respect to time. That is time angle. Time angle is always electrical angle only. Time angle is always electrical. There is no mechanical time angle. But space angle can be either mechanical or electrical, but in mathematical equations we must use always electrical. Okay, so two important points. Space angle can be either mechanical or electrical, but we must use always electrical. Time angle is always electrical only. Okay, fine. So how to reverse the phase sequence of voltage generation in a synchronous machine? By reversing the rotation of rotor. When rotor rotation is reversed, phase sequence will also reverse. Okay. All right. Let us now discuss about the next concept. This is about stator and rotor field analysis. Okay. Very simple concept. I will do it for both generator as well as for motor. Okay. So listen very carefully. Now first let me consider a synchronous generator. Assume this is the stator part of the synchronous generator. For the analysis purpose, I will only consider one coil, one phase. And the same concept is applicable for any number of phases and for any number of coils. Assume we have a coil A dash here, very clear. Now this is the stator part, inside which a rotor magnetic circuit is there. Okay, this is the rotor magnetic circuit, and this rotor is excited using which supply? DC supply, to create a time invariant field. And assume the polarity of the time invariant field is north pole here and south pole here. And I am also assuming rotor is rotating in anti-clockwise direction. It all depends upon the prime mover direction. By default, I am assuming the rotor is rotating in anti-clockwise direction. So the first duty is identify the polarity of induced EMF in conductor A and A dash. Once again, use right hand rule. North pole will always emit the flux. Therefore, this is the direction of flux emitted by the rotor. Okay, fine. And field is rotating in anti-clockwise direction means with respect to field, conductor is said to be rotating in which direction? Clockwise. Therefore, A is moving to the right side. North pole is emitting the flux. EMF is out of the plane. So it is a dot polarity. It is a dot polarity. A dash will have a cross polarity. So we have induced EMF in conductor A and A dash. These conductors are nothing but armature conductors. Now tell me, whenever EMF is induced in armature conductors, okay, immediately current will be generated in case if a load is connected. Now look at this. Assume I have an alternator here. EMF is generated. The moment when EMF is generated, immediately current will generate, or load is compulsory? Yes, a load has to be connected. The moment when a load is connected, immediately a current will be generated. That current is called as armature current. And I told you in DC machines also, in case of a generating circuit, voltage and current will be always in same direction or opposite direction? Same direction. Because you see, Can I give the polarities like this based on the current flow? In this generator, what is the direction of current? Look at the arrow mark. This is the direction of current. In this load, the current is in downward direction. Then what about voltage polarity? I told you voltage polarity is always from minus to plus. This is the direction of voltage here, minus to plus. This is the direction of voltage here. So this element is right now generating the power or taking the power? Generating the power. This element is absorbing the power. Are you catching? In any element where power is generated, voltage and current will be in same direction. In any element where power is absorbed, voltage and current will be in opposite direction. Right now, I am talking about which machine? Generator. As it is a generating circuit, voltage and current will be in same direction. Therefore, if voltage is a dot polarity here, what about the current also? Dot polarity. If voltage is a cross polarity here, what about current also? Cross polarity. Therefore, tell me now, these armature conductors are right now normal conductors or current carrying conductors? Current carrying conductors. Stator conductors are carrying current because a load is connected. When these conductors are carrying current, we know any current carrying conductor can create magnetic field. How to find out the direction of magnetic field developed by these stator conductors? Please listen. The initial 10 hours of subject will be purely theoretical and analytic oriented. That analysis part you need to understand very carefully, then only numerical questions you can solve easily. Okay, so concentration is very important. Fine. So whenever you know current direction, how to identify magnetic field direction? So use right hand thumb rule. This conductor is carrying the current into the plane. This conductor is carrying the current out of the plane. So can I say this is the direction of stator magnetic field? Yes. So therefore, this is the direction of stator field. Why I am able to say this is a stator field? Because this field is developed by conductor A and A dash. They are nothing but stator conductors. Stator conductors will create a stator field. Now coming to this blue color line, what you are observing, can I say this blue color line is nothing but flux developed by this north pole and south pole? Flux developed by this north pole and south pole means that is rotor field or stator field? Rotor field. This is rotor magnetic field. Okay? Fine. So we have the direction of rotor magnetic field, and we have the direction of stator magnetic field. Very clear. What is the angle between the two right now? It looks like 90 degrees. Okay, fine. Now, my next question, don't forget we are talking about what? Generator. Now the next question. This rotor is a DC field or AC field? DC field. And I am rotating this rotor at how much speed? Synchronous speed. If any magnet is rotating with some speed, can I say along with that magnet, the magnetic field will also rotate with the same speed? Therefore, as rotor is rotating with a speed ns, definitely the rotor field will also rotate with the same speed ns. So, point is very clear. Rotor field is rotating with a speed ns. Why rotor field is rotating if I ask you? Because rotor is rotating. Okay, fine. Coming to stator field, tell me stator conductors are rotating or stationary? Stationary. If stator conductors are stationary, don't say stator field is also stationary. That is wrong. Even though stator conductors are stationary, stator field will rotate definitely. Why? Because we discussed in the entire induction machine course. Stator is a single phase winding or three phase winding. We will use three phase winding in armature circuit of synchronous machine. That too distributed winding. Yes, we studied. Whenever a balanced distributed winding is carrying balanced current, it will create a stationary magnetic field or rotating magnetic field. Rotating magnetic field. You remember that point? Yes. Definitely stator we will use three phase distributed winding. carrying three-phase balanced current. So whenever a three-phase distributed winding carrying three-phase balanced current, a rotating magnetic field will create. That's why stator field will also rotate at synchronous speed. Okay, why stator field is rotating in this direction? Because we know the sequence A, B, C. In the previous diagram I have shown you already. So it is in anti-clockwise direction, A, B, C. Okay, fine. So final questions. Why rotor field is rotating? Because rotor is rotating. Okay. Why stator field is rotating? Don't say because stator is rotating. Stator will never rotate. Stator core, stator winding stationary, but stator field is rotating because stator will have a three-phase distributed winding carrying three-phase balanced current. It will create rotating magnetic field. This is rotor field, this is stator field. Then what about resultant field? Resultant field means sum of the two. Sum of the two means I have to produce vectorial summation or algebraic summation. Vectorial summation because both are having a phase angle displacement. Okay, see, this is rotor field, this is stator field. In between the two, we have resultant field. This resultant field is also called as air gap field. Okay, also called as air gap field. It is the vectorial summation of stator field and rotor field. Now you tell me, rotor field is rotating with synchronous speed, stator field is also rotating with synchronous speed, then air gap field will also rotate with synchronous speed, because air gap field will be always between rotor field and stator field. Therefore, if both of them are rotating with ns, then air gap field will also rotate with ns speed. Okay, this is air gap field. Clear? Now answer few questions here. In the direction of rotation, if you see, in the direction of rotation, which field is leading and which field is lagging, or which field is flowing first and which field is following that field? Can I say, if you select in the direction of rotation, definitely rotor field is leading and air gap field is following that rotor field and stator field is following air gap field? Yes or not? So in the direction of rotation, rotor field is leading and stator field is lagging. In between the two, air gap field is there. So I can prepare a multiple select question here. In case of a synchronous generator, which of the following statements are correct? First statement, rotor field is leading air gap field. Correct or wrong? Correct. Air gap field is leading rotor field. That is wrong. Air gap field is leading stator field. Yes, that is correct. If I give another statement, stator field is leading air gap field, that is wrong, because here stator field is following air gap field. That means stator field is lagging, air gap field is leading. Rotor field is further leading. So therefore final conclusions are, in a synchronous generator, rotor field is leading air gap field, stator field is lagging air gap field. Okay, very clear. Now let us do the same analysis in case of a synchronous motor. Okay. Now this is same diagram I am selecting once again. Assume this is the stator part of the given machine. Stator has one coil A dash. Actually 3 phases will be there. I am considering one phase. Okay. Next. Assume this is the rotor magnetic circuit we have. Fine. Now this is the circuit I have selected. Once again, assume the rotor is rotating in anti-clockwise direction. Now your first duty is find out the polarity of EMF in conductor A and A dash. As field is rotating in anti-clockwise direction, conductors are relatively moving in clockwise direction. Therefore, A will move to the right side, north pole will emit the flux, so EMF is out of the plane. And here EMF is into the plane. But I am talking about a generating circuit this time or motor circuit. We are talking about a motoring circuit. Yes, we just discussed motoring machine means it is a machine where power will be absorbed or power will be generated. Yes, power will be absorbed from the source. Power is absorbed means voltage and current will be in the same direction or opposite direction? Opposite direction. That's why motor voltage is called as a back EMF. I hope you remember in DC machine we discussed. Motor voltage is called as back EMF. Current will be opposite to the direction of EMF. So therefore, if EMF is a dot polarity, current polarity becomes cross polarity. Here, if EMF is a cross polarity, current polarity becomes dot polarity. Yes or not? Now, we got the polarity of the current carried by stator winding. If you know direction of stator current, can you find out direction of stator field? Right hand thumb rule. According to that, current is into the plane here, out of the plane here. So can I say stator field is along the thumb of right hand? So therefore, this is the direction of stator field. Okay, I am not there are no magics here, simple right hand thumb rule. What is the direction of rotor field here? Rotor field means the field produced by these two poles. Always north pole will emit the flux. Therefore, this north pole is emitting the flux. This is rotor field. Next, rotor field is stationary or rotor field is rotating? Definitely the rotor field is rotating because rotor is rotating by prime mover. So, rotor field is rotating in anti-clockwise direction. Coming to stator, stator field is stationary or stator field will rotate? Definitely stator field will rotate. Why? Don't say stator is rotating. Stator field is rotating because stator is a three-phase balanced distributed winding carrying three-phase balanced AC currents. Therefore, automatically rotating field will create. Stator field is rotating. This is rotor field, this is stator field, then where will be the resultant field or air gap field? In between the two. So, can I say the vectorial sum? This is nothing but air gap field. It is the vectorial summation of rotor field and stator field. If these two fields are rotating with synchronous speed, then air gap field will also rotate with synchronous speed because air gap field is always in between stator field and rotor field. Now you look at this diagram, you just understand in the direction of rotation, tell me which field is leading this time. Yes, stator field is leading and rotor field is lagging. In generator, rotor field is leading, stator field is lagging. In motor circuit, stator field is leading, rotor field is lagging. Therefore, what is the final summary point for motor? In case of synchronous motor, stator field is leading air gap field, rotor field is lagging air gap field. In case of synchronous generator, rotor field is leading air gap field, stator field is lagging air gap field. So you have to remember these statements. Okay. So let me write down the statements once. So the observations are, in case of a synchronous generator, rotor field is leading, stator field is lagging. In case of synchronous motor, stator field is leading, rotor field is lagging. But one common point in the entire discussion, what is the speed at which all these fields are rotating? Stator field, rotor field, air gap field, all fields are rotating at synchronous speed. Stator field rotating at ns RPM. Okay, next. Rotor field rotating at ns RPM. Air gap field rotating at ns RPM. Okay, stator field, rotor field, air gap field, all are rotating at ns RPM speed. Okay, next, what is the speed at which stator is rotating at? Stator is rotating at how much speed? Stator means it is not stator field. Stator means it is a stator core, stator conductors, they are stationary. Am I right or not? Next, tell me what is the speed of rotor? rotor is rotating it. Tell me rotor means rotor core, rotor winding. Okay, rotor is stationary or rotor is rotating? Rotor is also rotating at how much speed? Synchronous speed. Okay, synchronous speed. So answer few questions from all these points. Try to answer few questions. Stator field is rotating at synchronous speed. Rotor field is rotating at synchronous speed. Air gap field is also rotating at synchronous speed. But stator core is not rotating, stationary. Rotor core is also rotating at synchronous speed. Now let me frame few questions for you. Okay, see here, I have selected 5 questions. You have to fill what are the answers here. This is the diagram reference for us, synchronous generator. And the same is applicable for synchronous motor as well. First question, the speed of stator field with respect to stator. First tell me, stator field is rotating at a synchronous speed, but stator core is stationary. Therefore, the speed of stator field with respect to stator winding is nothing but ns, right? So therefore, the answer for the first question is ns rpm. Because stator field is rotating at ns, stator core is stationary, relative speed is ns. Next, speed of rotor field with respect to rotor. Tell me, what is the speed at which rotor field is rotating? Ns. What is the speed at which rotor core is also rotating? Ns, in same direction, right? So rotor field speed is ns, rotor core speed is also ns. Therefore, what is the relative speed between the two? 0. Therefore, the answer for second question is 0. Next, speed of air gap field with respect to stator. Air gap field speed is ns. With respect to stator, stator means stator core, stationary. ns stationary. What is the relative speed? ns. Next one, speed of rotor field with respect to stator field. This is rotor field with respect to stator field. Rotor field speed is ns, stator field speed is also ns, in same direction. Therefore, what is the relative speed? 0. Is it nothing but the condition to be satisfied for the production of electromagnetic torque? We discussed many times. There are 3 conditions. Out of that, one condition is relative speed between stator field and rotor field must be always equal to 0. That is satisfied in synchronous machine. Relative speed between stator field and rotor field is equal to 0. Clear? Last question. Speed of air gap field with respect to rotor. Speed of air gap field with respect to rotor. Rotor in the sense rotor core. Air gap field with respect to rotor core. Air gap field is rotating with ns. Rotor core is also rotating with ns. Then what is the relative speed between the two? 0. The last question answer is also 0. Like that, you can answer any question if you have a complete idea about this diagram. So, in case of synchronous machine, all fields are rotating along with rotor. Stator is only stationary. Now, the same concept can be implemented in DC machine as well. Already we discussed in DC machine course. I know most of you might have forgotten that, and I will discuss once again, but because it is very important. In case of a synchronous machine, magnetic field is on rotor, armature winding is on stator, right? But in case of DC machine, magnetic field will be on stator, armature winding will be on rotor. So let us try to answer the same 5 questions with respect to DC machine. Okay, let us see. Okay, let me try to implement the same concepts for DC machine as well. I will go little quickly because we studied already. You see this? In DC machine, armature winding will be on rotor. Assume this is rotor. Magnetic field is on stator. This is a stationary stator. Assume I am selecting a 2-pole machine, north pole and south pole. And this armature will have a number of coils in it. I am selecting a few. Yes, first draw polar axis. The axis which is passing through the pole, this is nothing but polar axis. And this is going to be the interpolar axis. Now left side of interpolar axis, which pole effect? North pole effect. Right side of interpolar axis, south pole effect. And assume that this rotor is driven in clockwise direction using the help of a mechanical prime mover. Rotor is rotating in clockwise. Let me also give numbers for the coils. This is 1, 1 dash, 2, 2 dash, 3, 3 dash. Okay. Now tell me, conductors are directly moving this time. So this conductor 2 is moving in upward direction, clockwise. Magnetic field is from north pole to south pole. My central finger will show the polarity which is into the plane. Under south pole, the polarity will be out of the plane. The moment when EMF is induced, immediately current will circulate in case if a load is connected. If load is connected, current cannot circulate. Assume the load is connected, current started to circulate. Therefore, these rotor conductors are now normal conductors or current carrying conductors. Whenever they are carrying current, immediately what happens? Magnetic field will be created. So identify the direction of rotor magnetic field first. You see, this is rotor part. These three conductors are carrying the current into the plane. These three conductors are carrying the current out of the plane. Therefore, what my thumb is showing, direction of magnetic field. That is in which direction? Downward direction. Therefore, rotor field is in downward direction. Rotor field is in downward direction. Okay, this is rotor field. What about the direction of stator field? Stator field means it is the magnetic field developed by this north pole and south pole. We know flux is always from north pole to south pole. This is stator field. It is stator field. Now tell me, stator field is stationary or moving? Stator field is stationary. Why? Because stator is DC excitation first of all. And that too, stator core is always stationary. That's why stator field is always stationary. It won't move. In case of AC machine, why stator field is moving? Because in AC machine, stator will have three-phase distributed winding carrying AC current. That's why rotating magnetic field will create. But in DC machine, stator will have DC excited field. Therefore, stator field is stationary. Now what about rotor field? Rotor field is stationary or rotor field is rotating? Don't by default tell me, sir, rotor is rotating, that's why rotor field will also rotate. That is wrong. I discussed in DC machine already. Even though rotor is rotating, this rotor field remains stationary. If you remember, you can forward this video, otherwise try to listen. Okay. Now, why rotor field is stationary even though rotor is rotating is the question. Assume rotor is rotating at a speed nr or ns, whatever you take. If rotor is slightly rotated, can I say next time rotor is rotating in clockwise direction? Next time can I say 3 will go to 1 dash position, 1 dash will come to 2 dash position, 2 dash will come here, 3 dash will come here, 1 will go here, 2 will come here. Yes or not? This is all possible only if rotor conductors are rotating. Let me try to draw one more diagram. Stator poles won't change. This is north pole. Here we have a south pole. Coming to rotor, this is interpolar axis. Yes, tell me. This 3 will come to this position if rotor rotated in clockwise direction. This is conductor 3. This is 1 dash. This is 2 dash, 3 dash, 1, 2. Rotor is rotating in clockwise direction at a speed nr. Now tell me, earlier conductor 3 is under the influence of which pole? North pole. But now conductor 3 is under the influence of south pole. Therefore the polarity will change. Earlier conductor 3 dash, it is under the influence of south pole, dot polarity. But now conductor 3 dash is under the influence of north pole. This is cross polarity. Now use right hand thumb rule and tell me what is the direction of stator magnetic field and rotor magnetic field. Coming to rotor first, these 3 are into the plane and this is out of the plane. So rotor magnetic field is once again at the same location. Stator field is always from north pole to south pole. Therefore, from these two diagrams tell me, even though the rotor conductors are rotating, the rotor field position changes or not changed? Not changed by an inch also. You see, this is the rotor field position in case number 1 and this is the rotor field position in case number 2. So, even though rotor is slightly rotated, the rotor field remains stationary. Therefore, tell me now finally, in case of a DC machine, what is the speed of stator field? 0. What is the speed of rotor field? 0. Then what is the resultant? Air gap field. Air gap field means it is the resultant of stator field and rotor field. If these two fields are stationary, air gap field is also stationary. Yes or not? So, can you tell me answers for the same 5 questions? The first question is, what is the speed of stator field with respect to stator core? Stator field stationary, stator core stationary, therefore the relative speed is 0. Second question, what is the speed of rotor field with respect to rotor core? Can you tell me one thing? Rotor core is stationary or rotating? Rotating, but rotor field is stationary. So, what is the speed of rotor field with respect to rotor? That is minus NR. It is not plus NR, it is minus NR. Why it is minus NR? I will tell you one simple example. Imagine you are moving on your bike, okay, in a forward direction. Your bike is moving in a forward direction. Road is always stationary. But if you see that stationary road from your bike, how it looks like? Don't say, sir, we will never observe road. Okay, those kind of answers will not be valid here. Assume you are going on a bike and from the bike, if you see the road, how road looks like? Yes, the road looks like moving opposite to your bike. Am I right? But what is the actual fact? Your bike is moving, road is stationary. But if you observe that road from your bike point of view, it looks like road is moving in opposite direction. Similarly here, actual fact is field is stationary, rotor is rotating. But what is my question? What is the speed of rotor field with respect to rotor? Actually, rotor field speed is 0. But with respect to rotor, if you see, it looks like moving opposite to the direction of rotor. Okay, minus NR. Understand? I am repeating that question again. This is logical. What is the speed of rotor field? If I simply ask you, you will say, sir, rotor field is stationary, therefore its speed is 0. That is like road speed is 0. But my question is, what is the speed of rotor field with respect to rotor? That means, what is the speed of road with respect to your bike? With respect to your bike, can I say road is moving opposite to your bike? So it will be minus speed. Similarly, the speed of rotor field with respect to rotor is minus NR. Minus NR. Okay. Next. What is the speed of rotor field with respect to stator field? 0, because rotor field is stationary, stator field is stationary, therefore relative speed is 0. What is the speed of air gap field with respect to rotor? Once again, minus NR only, because air gap field is stationary, rotor is rotating, but if you calculate the speed of field with respect to rotor, that is minus NR, opposite. Okay. So likewise, you can answer any number of questions. So what is the difference you are observing from synchronous machine to DC machine now? In a synchronous machine, stator field rotating, rotor field rotating, air gap field rotating. In a DC machine, stator field stationary, rotor field stationary, air gap field stationary. That's all. We studied synchronous machine field concept, DC machine field concept also at the same time. In synchronous machine, all 3 fields are rotating. In a DC machine, all fields are stationary. In a synchronous machine, all fields are rotating at the same speed, ns. In a DC machine, all fields are stationary, 0. Now, let me implement the concept for induction machine also at the same time, so that all 3 machines together we can frame some summary points. Okay. Let me discuss about induction machine field concept also. I think most of you might have remembered, okay, because we studied induction machines already. We studied about field concept in induction machine already. Let me discuss here. The simplest point is stator is always stationary. I hope you remember this diagram. Stator will have a three-phase distributed winding, excited using positive sequence supply with a frequency F and a number of poles P. Whenever a three-phase distributed winding is excited with three-phase balanced supply, immediately rotating magnetic field will produce at how much speed? Synchronous speed. So this is synchronous speed. This is the speed of stator or stator field. That is the speed of stator field. Clear? Next. Rotor will rotate exactly at synchronous speed or near to synchronous speed? Near to synchronous speed. This is rotor. What is the frequency of rotor? Slip frequency. Therefore, the rotor field will rotate at slip speed. This is ns minus nr. This is the position of rotor field. If you remember this diagram, you can answer any question from induction machine as well. So, answer my questions here. What is the speed of stator field with respect to stator? Ns. What is the speed of rotor field with respect to rotor? Ns minus nr. What is the speed of rotor field with respect to stator? Nr plus ns minus nr. Overall it is ns. What is the speed of rotor field with respect to stator field? 0. Okay, relative speed is 0. Therefore, you see, from the past half an hour, 40 minutes, we studied field concept in synchronous machine, DC machine, induction machine. All three rotating electrical machines at the same time. What are the common summary points? In synchronous machine, stator field, rotor field will rotate at the same speed, ns. In DC machine, stator field, rotor field both are stationary. In induction machine, stator field is rotating with ns, rotor field is rotating with ns minus nr, but ultimately the relative speed is always 0. What about air gap field? If you add both of them, air gap field will also rotate at the same speed. This is air gap field. Okay, it will also rotate at how much speed? Synchronous speed with respect to stator. And how much with respect to rotor? Ns minus nr with respect to rotor. So, let me create a question here. Okay, question number 1. What is the speed of stator field with respect to stator in synchronous machine? Ns. What is the speed of stator field with respect to stator in DC machine? 0. What is the speed of stator field with respect to stator in induction machine? Ns. Next question. What is the speed of rotor field with respect to rotor in synchronous machine? I don't have diagram here. It is on the other board. Please try to imagine. What is the speed of rotor field with respect to rotor? 0, because rotor field is rotating with ns. Rotor is also rotating with ns. Therefore, relative speed is 0. That is in synchronous machine. What is the speed of rotor field with respect to rotor in DC machine? Minus nr. Okay. What is the speed of rotor field with respect to rotor in induction machine? Ns minus nr. Third question. What is the speed of rotor field with respect to stator field in induction machine? 0. What is the speed of rotor field with respect to stator field in DC machine? 0. What is the speed of rotor field with respect to stator field in synchronous machine? Also 0. So that 0 condition will be satisfied in every rotating electrical machine, because that is the condition to be satisfied for the production of electromagnetic torque. What is that condition? Relative speed between stator field and rotor field must be equal to 0. So likewise, if you are able to analyze these diagrams carefully, you can answer any kind of question with respect to field speeds. Okay? Fine. Let me conclude the lecture here. In the next lecture, we will start discussing about construction part of synchronous machine. Okay? Thank you.